Okay, here is question number 2 at the end of chapter 5 about a painting station, and they spray steel panels. The first piece of information that the problem gives you is the arrival rate, which is they arrive at 12 panels per hour with inter-arrival times with a coefficient of variation of 1. So I'm going to take that 12 panels per hour and I'm going to put that in a minute format. I'm going to divide 60 divided by 12 per hour gives us 5 panels per minute, with the coefficient of variation of the arrival time about 1 minute. The painting time has an average of 4 minutes, standard deviation of 4 minutes. So the effective and the theoretical times are the same at 4 minutes because there's no supporting time here. So with no supporting time, or if supporting time is 0, then the effective and the theoretical are the same. Also, the standard deviation is about 4 minutes. So the effective coefficient of variation of the process time is also 1, because that is 4 standard deviation divided by 4 minutes of the effective process time. First question, part A. What fraction of an hour is the painting sprayer idle? What time are they waiting for is the sprayer waiting for panels? We're going to calculate that using the utilization. And we have the formula for the utilization is our effective process time divided by the arrival process time times the number of resources. In this case, there's one sprayer, one spray painting machine. That gives us 0.8. So if we take 1 minus 0.8, that gives us a 0.2, or 12 minutes per hour of being idle. That answers part A, about 12 minutes per hour. Question B. If the machine requires an adjustment after working for 90 minutes, with a standard deviation of 90 minutes, and the adjustment takes an average of 10 minutes, with a coefficient of variance of 1, does that change the idle time? So we'll take our 90 minutes mean time before failure as MF. We'll take a 10-minute average time to repair. That gives us an availability of 0.9. The coefficient of variation for that repair is 1. And so we'll take the theoretical time, which is still 4, divide by the availability to get our effective mean process time, given this scenario of adjustments. Again, we'll use the utilization, but this time we'll use this effective process time, which takes into account the repair. So we'll take that 4.44 divided by the arrival rate times the number of resources. And that gives us 0.89. And if we multiply that out, we find that that is a 6.6 minutes of idle time. So we went from 12 minutes to 6.6 minutes, 6.7 minutes. Almost cut in half, due in large part to the difference in availability and that repair time. Moving on to part C. Answer again, what is the idle time? But in this case, after completing a panel, there's an 8% chance the spray machine needs an adjustment that takes 5 minutes with standard deviation of 12 minutes. Okay, so there's an 8% chance of an adjustment, a setup. We'll call that a setup for the purposes of our of our circumstance here and using these formulas. So what does that mean? We can take that 1 divided by 8%, and what that tells us is that gives us the average number of jobs between setups. And that's pretty key here. And the reason why we can do that is because of this 8%. So there's an 8% chance after completing each panel that there needs to be an adjustment. We can take that percentage, that percent chance, and we do 1 divided by 8%, and we can actually find out the number of jobs between setups. And that gives us our N, 12.5 jobs on average between setups, right? There's a 1 in 8 chance. So if we do 1 in 8, we 1 divided by 8% will give us 12.5 number of jobs between setups. If the adjustment time is 5 minutes, the average adjustment time with a 12-minute standard deviation, and we still have our theoretical process time of 4 minutes and our standard deviation of the process time of 4 minutes, we can calculate the effective mean process time by taking that theoretical, adding the average adjustment time divided by the number of setups. This is equation 5.7 in the book, page 203, where we're looking at the effective process time for task-based interruptions. That's the formula that we're using here. So this formula for effective process time is task-based, and the formula up here was a time-based equation for part B. And we're seeing here the different formulas that we need to use depending on the type of interruption. In this case, in part C, it's a task interruption. We know that after 12.5 jobs, we're going to need a repair. And that's not time-based, that's task-based. So again, that formula for effective process time for task-based interruptions is we take that theoretical process time of 4 minutes, we add the average adjustment time of 5 minutes divided by the average number of jobs between setups, which in this case is 12.5, and that gives us an effective mean process time of 4.4 minutes. Then we can go to utilization. We can take that utilization is the effective process time divided by the number of machines times the arrival rate, and that gives us a utilization of 0.88, which calculates out to a 7.2 minute in 60 minutes time of idle based on this type of task interruption. And then finally, part D, which one of the cases in part B or C results in longer waiting times for panels in the painting station? Okay, so we are going to calculate the coefficient of variation, the effective variability for both the time-based interruptions and the task-based interruptions. We're going to use this equation for the time-based, and we'll use these two equations for the task-based. So we have the coefficient of variation, the effective variability. We have the effective variability for the repair. We have the availability. We have the repair time, which on average is 10 minutes, and we have the theoretical process time. Those are all the inputs that we need following this formula right here to calculate the effective variability squared, which is 1.45. We do the square root of that number to calculate what the effective variability is for time-based interruptions for part B, and that is 1.2. For part C, we're doing strictly a task-based interruption, so we have different formulas to calculate the effective variability. We need this information to calculate this squared standard deviation. And then we take the square root of that divided by the effective process time to find the coefficient of variation for the effective variability. So here's our 12.5, average number of jobs between setups. Here is our 5 minutes of average adjustment time. Here is our 12 standard deviation of adjustment time. It takes about 12 minutes of standard deviation from part C. Here is the standard deviation of the process time itself, which is 4 minutes. So this is minutes, this is minutes, this is minutes, and this is number of jobs. We take these inputs and we plug them into this equation here, which gives us 29.36. Again, that's the squared effective standard deviation. We take the square root of that, and that gives us 5.42, and this is also minutes. What does that mean? That's the effective standard deviation of the variation. And we use that in this equation. We are pulling the 4.4 minutes from here, the effective mean process time based on task-based interruptions, to calculate the coefficient of variation here. The effective variability is standard deviation divided by the mean, which is 1.23. Notice that this is very close to the 1.2. So it turns out that these processes are very, very similar. We also see that in the idle time as well. Pretty close idle times for these two different scenarios for this painting station. And that concludes this problem.